Download this code from codegive.com, link in the description below. Bandwidth limitations on fiber optics in audio, a deep dive. Fiber optic technology has revolutionized audio transmission, offering significant advantages over traditional copper-based systems. Its high bandwidth, immunity to electromagnetic interference, EMI, and low signal loss make it ideal for high-fidelity audio applications, especially in professional audio, recording studios, and large-scale sound reinforcement systems. However, even fiber optic systems are not without limitations. Understanding these limitations and how they impact audio quality is crucial for designing and implementing robust fiber optic audio solutions. This tutorial will cover 1. Introduction to fiber optics for audio *, the basics of how fiber optics work and their advantages for audio applications. 2. Bandwidth concepts *, a refresher on bandwidth and its relationship to audio signal quality. 3. Key limiting factors *, detailed explanation of the factors that limit bandwidth in fiber optic audio systems, including fiber type multi-mode versus single mode, dispersion chromatic and modal dispersion, attenuation signal loss within the fiber, transmitter/receiver characteristics laser diode characteristics, photodiode sensitivity and electronic processing speed, connectors and splices losses and reflections introduced by connectors and splices, protocol and encoding the impact of digital audio protocols and encoding schemes. 4. Impact on audio quality *, how bandwidth limitations manifest as audible artifacts or performance degradation. 5. Mitigation techniques * strategies to minimize the effects of bandwidth limitations. 6. Code example, Python simulating bandwidth limited audio transmission and analysis. 7. Conclusion * summarizing key takeaways and future trends. 1. Introduction to fiber optics for audio. Fiber optic cables transmit data as pulses of light through thin strands of glass or plastic. The basic components of a fiber optic system are transmitter converts electrical audio signals into optical signals, light pulses, using a laser diode, or LED in some lower performance systems. Fiber optic cable the medium for transmitting the light pulses. Receiver converts the optical signals back into electrical audio signals using a photodiode. Advantages of fiber optics for audio high bandwidth fibers can carry significantly more data than copper cables, enabling transmission of high-resolution audio formats like DSD and high sample rate PCM. Immunity to ME/RFI optical fibers are immune to electromagnetic interference and radio frequency interference, ensuring a clean and noise-free signal. This is particularly crucial in environments with strong electromagnetic fields, example near power lines, radio transmitters. Low signal loss fiber optic cables exhibit significantly lower signal attenuation, loss, over long distances compared to copper cables. This allows for longer cable runs without signal degradation. Security fiber optic cables are difficult to tap into, providing a more secure data transmission pathway. Ground loop isolation fiber optic systems inherently isolate equipment grounds, preventing ground loops and associated noise. 2. Bandwidth concepts. Bandwidth, in the context of audio, refers to the range of frequencies a system can accurately reproduce. It's typically measured in hertz, or megahertz, megahertz. Analog audio the bandwidth is the range of frequencies the analog audio signal occupies. For high-fidelity audio, a bandwidth of at least 20 Hz to 20 kHz is desired to cover the full range of human hearing. Higher bandwidth may be required for ultrasonic information sometimes present in recordings, example DSD. Digital audio in digital systems, bandwidth relates to the data rate of the digital audio stream. Higher sampling rates and bit depths require higher data rates, and therefore, higher bandwidth capacity in the transmission system. The Nyquist-Shannon sampling theorem states that the sampling rate must be at least twice the highest frequency component in the audio signal to avoid aliasing. 3. Key limiting factors. Even though fiber offers high bandwidth, several factors can limit the practical bandwidth available for audio transmission. 3.1. Fiber type, multi-mode versus single mode. Multi-mode fiber, MMF has a larger core diameter, allowing multiple light rays, modes, to propagate through the fiber. MMF is generally less expensive and easier to work with but has a lower bandwidth and shorter transmission distance compared to single-mode fiber. MMF is often used for shorter distances, example within a studio. Single-mode fiber, SMF has a very small core diameter, allowing only a single mode of light to propagate. SMF offers significantly higher bandwidth and can transmit data over much longer distances. SMF is typically used for long-haul telecommunications and broadcast applications. The key difference affecting bandwidth is modal dispersion, see below. 3.2. Dispersion. Dispersion refers to the spreading of light pulses as they travel through the fiber. This spreading limits the bandwidth because it can cause adjacent pulses to overlap, making it difficult for the receiver to distinguish between them. Two main types of dispersion affect fiber optic systems. Chromatic dispersion. Different wavelengths of light travel at slightly different speeds through the fiber. Because light sources, even lasers, emit a range of wavelengths, this causes the light pulses to spread out over time. Modal dispersion. Primarily in multi-mode fiber. Since multiple modes of light travel through MMF, each mode travels a slightly different path length through the fiber. This causes the different modes to arrive at the receiver at slightly different times, leading to pulse spreading. Modal dispersion is the dominant limiting factor in MMF systems. SMF largely eliminates modal dispersion, enabling much higher bandwidth. Dispersion is measured in picoseconds per nanometer per kilometer, ps/nm/km. A higher dispersion value indicates greater pulse spreading. 3.3. Attenuation. Attenuation is the loss of signal strength, optical power, as light travels through the fiber. Attenuation is caused by absorption, scattering, and bending losses within the fiber. Excessive attenuation reduces the signal-to-noise ratio, SNR, at the receiver, which can limit the maximum data rate and audio quality. Attenuation is typically measured in decibels per kilometer, dB/km. Lower attenuation values are better. 3.4. Transmitter/receiver characteristics. The performance of the transmitter and receiver plays a critical role in determining the overall bandwidth of the system. Laser diode characteristics. Spectral width. The range of wavelengths emitted by the laser diode. A narrower spectral width reduces chromatic dispersion. Rise and fall times. The speed at which the laser diode can turn on and off. Slower rise and fall times limit the maximum data rate. Output power. Insufficient output power can lead to a low SNR at the receiver. Photodiode sensitivity. The ability of the photodiode to detect weak optical signals. Lower sensitivity requires higher optical power at the receiver. Asterisk electronic processing speed asterisk the speed at which the transmitter and receiver can process the electrical signals. Slower processing speeds limit the maximum data rate. 3.5. Connectors and splices. Connectors and splices introduce losses and reflections in the fiber optic system. Asterisk losses asterisk connector and splice losses reduce the signal strength and can contribute to a lower SNR. Asterisk reflections can interfere with the transmitted signal and cause errors. High-quality connectors and proper splicing techniques are essential to minimize these effects. 3.6. Protocol and encoding. The digital audio protocol and encoding scheme used can impact the required bandwidth. Asterisk digital audio protocols asterisk protocols like AES/EBU, A.Lightpipe, TSLink, MADI, and Dante have different data rates and bandwidth requirements. Some protocols are more efficient than others. Asterisk encoding schemes asterisk the way audio data is encoded can affect the bandwidth. For example, uncompressed PCM audio requires a higher data rate than compressed audio formats like MP3 or AAC. Asterisk overhead asterisk protocols introduce overhead, example header information, error correction codes, which consumes bandwidth and reduces the effective data rate available for the audio signal. 4. Impact on audio quality. Bandwidth limitations can manifest as various audible artifacts. Asterisk reduced high-frequency response asterisk if the bandwidth is insufficient, high-frequency components of the audio signal may be attenuated or lost, resulting in a dull or muffled sound. Asterisk increased distortion asterisk nonlinearities in the transmitter or receiver, combined with bandwidth limitations, can introduce harmonic distortion, making the audio sound harsh or unnatural. Asterisk aliasing asterisk if the bandwidth is too low to support the Nyquist rate, aliasing artifacts can occur, creating unwanted frequencies that were not present in the original audio signal. This sounds like metallic ringing or digital harshness. Asterisk increased noise asterisk a lower SNR due to attenuation or other factors can result in increased noise levels, making the audio sound grainy or hissy. Asterisk data errors asterisk in digital audio systems, bandwidth limitations can lead to data errors, resulting in clicks, pops, or dropouts. 5. Mitigation techniques. Here are some strategies to minimize the impact of bandwidth limitations. Asterisk use single-mode fiber asterisk whenever possible. Use single-mode fiber to minimize modal dispersion, especially for longer distances. Asterisk choose high-quality components asterisk use high-quality laser diodes, photodiodes, connectors, and cables to minimize losses and improve performance. Asterisk proper installation and termination asterisk ensure proper connector installation and splicing techniques to minimize losses and reflections. Use professionally trained technicians. Asterisk optimize transmission distance asterisk keep cable runs as short as possible to minimize attenuation and dispersion. Asterisk use appropriate protocols and encoding asterisk choose digital audio protocols and encoding schemes that are efficient and suitable for the application. Avoid unnecessary overhead. Consider lossless compression if bandwidth is a critical constraint. Asterisk equalization and signal processing asterisk implement equalization techniques to compensate for frequency response variations caused by bandwidth limitations. Signal processing algorithms can be used to reduce noise and distortion. Asterisk wavelength division multiplexing, WDM for very high bandwidth applications. WDM can be used to transmit multiple optical signals at different wavelengths over a single fiber. 6. Code example, Python simulating bandwidth-limited audio transmission and analysis. This example uses Python and the NumPy, SciPy, and Matplotlib libraries to simulate the effect of bandwidth limitation on an audio signal. It demonstrates a simple low-pass filter to represent the bandwidth limit and then analyzes the resulting signal in the frequency domain. Explanation **. One load audio file * loads an audio file using scip.io.wav file.read. Replace your _audio file.wav with the path to your audio file. Handles stereo files by taking only the first channel, mono. To define parameters * sets the cutoff _frequency, bandwidth limit, and the filter _order. Adjust these values to experiment with different bandwidth limitations. 3. Butterworth filter design * defines functions to design and apply a Butterworth low-pass filter. Butterworth filters are chosen for their flat frequency response in the passband. 4. Apply filter * applies the low-pass filter to the audio data, simulating the bandwidth limitation. 5. Frequency domain analysis * uses the fast Fourier transform, FFT, to analyze the frequency content of the original and filtered audio signals. The analyze _spectrum function calculates and plots the magnitude spectrum. The plt.slim limits the plot to the Nyquist frequency. 6. Time domain analysis * plots the original and filtered audio signals in the time domain. This allows you to visually compare the waveforms. 7. Save filtered audio * optional, saves the filtered audio to a new WAV file. How to use * 1. Install libraries * make sure you have the required libraries installed. Run. 2. Replace file name * replace your _audio file.wav with the correct path to your audio file. 3. Run the script * execute the Python script. 4. Analyze the results * the script will generate plots showing the spectrum of the original and filtered audio. Listen to the filtered _audio.wav file to hear the effect of the bandwidth limitation. Experiment with different cutoff _frequency values to observe how it affects the audio quality and the frequency spectrum. Observations **. You'll see that the filtered audio spectrum has significantly reduced amplitude above the cutoff _frequency. The time domain plot will show that the high frequency components of the signal are attenuated in the filtered audio. Audibly, you'll notice that the filtered audio sounds duller and has less high frequency detail compared to the original audio. The degree of the effect depends on the chosen cutoff frequency. 7. Conclusion. Fiber optics offer substantial advantages for audio transmission, but understanding and mitigating bandwidth limitations is crucial for achieving optimal audio quality. Factors like fiber type, dispersion, attenuation, transmitter/receiver characteristics, connectors, and protocols all play a role. By carefully selecting components, implementing proper installation techniques, and employing appropriate signal processing methods, you can maximize the bandwidth and performance of your fiber optic audio systems and ensure high-fidelity sound reproduction. Future trends **. Higher bandwidth technologies * research continues on developing higher bandwidth fiber optic technologies, such as advanced modulation techniques and new fiber designs. Improved components * manufacturers are constantly improving the performance of laser diodes, photodiodes, and other components to increase bandwidth and reduce losses. Software-defined networking, SDN is being explored to dynamically allocate bandwidth resources in fiber optic networks, optimizing performance for audio and other applications. Quantum communication * while still in early stages, quantum communication technologies hold the potential to provide even higher bandwidth and more secure audio transmission in the future.